Apache Cassandra, you've got a nice tool called Op Center, and it does the repairs for you. And in the latest version of DataStax Enterprise, you've got something called Node Sync. I'm not sure how it works. It's quite secretive. They don't tell us how, but it just manages your repairs for you. There's something called Cassandra Reaper. So who's using Cassandra Reaper here? Anyone? Yeah, a few people. I used to go up to Spotify quite a bit to help them out in Stockholm. And it was actually Spotify who developed Cassandra Reaper. The reason why it's called Reaper is because one of the Swedish guys was developing the product couldn't pronounce the word repair, and someone interpreted it as Reaper, so it became Cassandra Reaper. So there you go. That's what they told me. Okay, so they wrote this repair system. It's really good, and it manages your repair for you. It's free, open source. Download it, and you can use it for your Apache Cassandra clusters. We tend to kind of use our own repair system using something called Rundeck. So we write our own kind of mechanism and use Rundeck for invocation. I don't know if you know Rundeck, but it's a scheduling system. And it's kind of manages the scheduling across all of your servers, automates them, and reports them, and reports on any issues when they happen. Integrates with things like Slack. So I can see all of our customers' repairs happening correctly, and then they get dropped into our Slack channels. So we have a confidence of when things are working correctly with repairs. We like that kind of a chat ops approach to managing clusters. So backups. Again, DataStax Ops Center provides enterprise-grade backup solution, and they have a scheduler that allows you to back up to your snapshots and copies that across to your remote locations like S3 or remote file systems. We tend to again use our own kind of backup mechanism using and invoke it using Rundeck, but you know we can use cron jobs or anything else you like. But backups can be fairly complicated with Cassandra because you've got a mechanism called snapshot, which creates hard links of your SS table files. Then you have to copy them across. But when a lot of the files don't change over time, so you've got to have a mechanism of deduping your data in your backups. Otherwise, your backup starts to explode in size. So those are some of the regular tasks that we have to do for Cassandra in enterprises. Some irregular tasks, so scaling, so provisioning new nodes, adding new nodes, new data centers, decommissioning, cleanup operations like garbage collect, node tool cleanup, a number of cleanup operations you do around your data. Tuning. So as you kind of gather your metrics and you see how well your cluster is performing or how they're not, based on those kind of performance metrics, you can tune your Cassandra in many of them in Cassandra.yaml files or even jvm.options file. So you can tune your GC and so on. But yeah. These are some of the operations tasks that we do. Patching, upgrades. There hasn't been many patches in the open source world, so we've been fairly lucky for managed services vendor that we didn't have to do a huge amount of patching of Apache Cassandra. We're up to 3.11.4 now with the latest version. We've been waiting for 4.0 to come out for a long time, but yeah, it's been threatening, and no, it's not there yet. So some of the tools that we discussed here, we've been using things like Grafana. Yeah, we like Grafana. It gives you great kind of dashboarding capabilities. Prometheus or InfluxDB, OpenTSDB, kind of a time series database to store all of your telemetry data. Elastic Kibana Log-Stash-Elk for storing your events and searching those. Yeah, so all of these tools are open source. We've used them heavily. So at the beginning, we have used all of these kind of open source tools to manage our customers' deployments. And it ended up looking something like this. So we've got a Cassandra node, and then we're using lots and lots and lots and lots of monitoring tools to manage our Cassandra servers. And actually, we were spending more time managing the monitoring tools than the Cassandra servers themselves. The patching cycle of all of these tools was crazy. Just we're in a patching hell all the time. Especially in heavily regulated industries like banks and insurance companies, where change is extremely difficult, right? You have to raise the change requests, get them approved, yeah, it takes a lot of effort in trying to make changes in these enterprises, right? Network changes like firewall configurations. So to initially deploy something like this, we have to open up the firewall ports for all of these connections that you can see in the diagram. And then you go to the infrastructure team requesting the firewall changes, and they get it wrong, and then trying to find where the problems are. It just became more and more difficult. And hands up who kind of experienced something like this. Yes, yeah, quite a lot of people. And the patching hell, right? So we decided we need to do something about it. So we made a wish list of all the things that we wanted out of the monitoring tools for managing Cassandra for our customers. We wanted it to be either on-premises or cloud. We wanted a unified dashboarding, not just, so we were sick of like switching between different tabs for logs and the events and the metrics and availability for various environments. So you have 4 tabs for each environment, right? We wanted a single system that managed our Cassandra, DSE, Kafka, Confluent, and all the products that we manage, rather than a plethora of tools, monitoring tools to manage them. We wanted to be domain aware. So we wanted it to be not like Datadog or other kind of generic monitoring tools, which are kind of passive in nature. They take information, they dashboard it, they alert you, but they don't do anything about it, right? You have to have a human involved. So we wanted a system that does active management of the systems based on the metrics and the logs and everything else that we capture. We also wanted a simple deployment model. We wanted to get away from this patching hell and the firewall hell and so on. So we decided to build our own system to do all this, and so we did, and we got a single pane of glass now that does all of the kind of metrics and dashboarding and operations like backups and repairs, alert notifications, all in single package with a very simple deployment model. So single agent, not like 6 different agents running on the box, with a single server and GUI, and to manage Cassandra and others. And we're using Elasticsearch for the storage of the telemetry data and logs. We didn't want to write an entire database for this, so we decided to use Elasticsearch for the time being. And it's actually given us a mechanism to deploy into our customers' environment very quickly. So we're slowly migrating the old customers that were on the other types of monitoring platform to this system. We do backups and we do repairs. So we built something called adaptive repair. Because we're capturing the telemetry around how the cluster's performing, things like CPU utilization and throughput and latencies, we can actually slow down the repair process and then speed up when there's resources available to try and complete the repair process within the GC grace seconds. Okay, so the kind of Reaper and other kind of repair mechanisms, they're not aware of the performance of the cluster. Whereas we've got, because we're collecting the metrics, we can actually kind of understand the state of the cluster and then tune the speed accordingly. So we call it adaptive repair. And backups, we've got backups in there as well. So we wanted a simple backup solution to be able to push the backups into AWS and so on. It also has notification integrations to the notification systems, so PagerDuty, email, Slack, etc. So yeah, it does all the things that we want to do in a single package, and we're very happy. We've decided to share the tool for open source community up to six nodes clusters. So if you're interested, you can download the product and start using it. It's still beta, so be interested to hear whether you would like to us to kind of continue developing it and distributing it. So that's me. Thank you very much.
So for questions, anyone? We have like 5 minutes. This is the box, by the way. Anyone? Questions? Okay. Microphone, so it's recorded. Yeah, we have people live stream, so.
Hello. So just curious how you mix and match the data from things like Elasticsearch and Kafka with the things like from DataStax and Cassandra. Is that difficult in terms of the different things that come from, or are they all JMX?
So we built a Java agent for each of those products. And then we've got essentially a node agent, which is written in Golang. And they talk to each other, the Java agent and the sort of native agent. And then all of the metrics get pushed rather than kind of a polling mechanism like Prometheus. Yeah, we didn't like the pull method. We wanted all of the metrics and logs and everything to go out as a push. So that's what we've done. So essentially, it's the same mechanism for all of those products. And then, although the free version currently doesn't have the ability to dashboard the Elasticsearch and Kafka yet, but internally we've got that already. And then we're going to start sharing those out once we think they're functionally ready for public consumption.
Cool, thanks. Do you want me?
Hi, Jackie.
Just wondering whether you see this being able to be federated out with the other challenger banks. So really impressive what's gone on here, and given some of the technical debt some of the other banks are carrying, can you see this being a sector play as well, given you've done what you've done? You know, I'm thinking of open banking, PSD2, all of that type of thing.
So the tooling is really just kind of focused on those types of products at the moment. Yeah, so but we haven't made this generic like Grafana and Prometheus. But we'll see how this goes. Really, I mean, if people find it useful, then we're going to spend a bit more time kind of developing on it. So and make it more generic as the time goes on.
Cool. Yeah.
1 2 1 2. Oh, silence. Okay, good evening, everyone. I'm Cédric Lunven. I'm developer advocate for DataStax during the day. And at night, I'm an open source contributor. So I created an open source framework named FF4J 5 years ago. And I'm actively contributing to another framework, gHipster. And I bring with me quite a lot of swag today, and you can have some swag later after my talk when you leave. I think there is some backpack stickers, maybe even 1 or 2 t-shirts like that. So we are together for 30 minutes, about 30 minutes. I have 4 objectives with you, so we will check after that if I got everything. So first, this is my first time in London doing some meetups. So I would like to remember you all the free resources available to you online, just for you to improve with Cassandra, Apache Cassandra, and get some pretty nice applications. So first, of course, you expect me to put that link at first, DataStax Academy, where you can find all the training around Apache Cassandra for free. Here we got maybe now 100 hours of video about Apache Cassandra and all the ecosystem of DataStax. The developer blog is also there, so have a look. We also have a lot of small demo and stuff like that. Okay, another stuff, maybe more fun. Every Wednesday, we release a video. We have a YouTube channel, DataStax Academy, and every week we released 10-minute long video around Apache Cassandra and distributed system overall. Can talk about distributed graph, can talk about or NoSQL DB. So bring your phone, you will have a couple of pictures to take tonight. So this is the first one. Second one, every Tuesday at 5:30 UK time, London time. So 6:30 for me, I'm French. You may have tell with my ugly accent, right? Okay, so we are giants, we are motivated, we bring a lot of energy, so we are doing Twitch. Yes. So we're doing some live streaming, developing applications around Apache Cassandra. And this is what I will do tonight. This is not all about slides. And the most, at least for my team as developer advocate, we provide some reference applications, so full working applications. So killer video, I will provide you another links later. So it's a sample application available in 4 languages, Java, C#, Python, and Node.js, with all you can expect from developing on top of Cassandra. You have the mapper, you have the connecting, you have all the workloads present in DataStax product, but nevertheless, you have everything you need to work with Cassandra. And last but not least, once a year, we organized an event. We call that the Developer Days. Last year, it was on November the 6th. So a full day, you came, it's free. Full day, hours of demo workshop for you to have hands-on on the product. And again, last pictures for you. Take that GitHub repository, a lot of sample code for IoTs, for CRUD applications, a lot of things. And the author is in the room. most of the samples on the data stacks code samples came from you, sir. Okay, so that's it. 5 minutes just to remind you, free available, take some pictures. So what about the topic today? I would like to show you and provide you an API. It's all about the topic, implemented with 3 different technologies, but it's the same API and working on top of Apache Cassandra. So it's provided in REST, GraphQL, and gRPC. Okay, so it's easy to remember. GitHub, clone, Meetup, Cassandra. I will send an email on the user group with all the slides and on SlideShare if you need to, and if you have no room in your phone to take photo. Okay, so let's start. You want to develop an API, sure. So if you already work with Apache Cassandra, you know you always start with the data model, no exceptions. Again, people, oh, I'm using a relational database and I will start with developing service. No, always start with the data model. Create your good tables, partition, key, clustering column, know your stuff. It's always the data model at first. And only then we will try to figure out how we implement the API using those 3 technologies. But always start with the data model. And then the plumbery, I won't get into the details tonight with you, but here it is. I won't show that code to you. So if you have seen the training on Academy regarding data model, you may have already seen that kind of workflow saying that to implement my data model on Apache Cassandra, I need first to know my conceptual data model, then my queries, and using some magics, I can create some mapping, logical, physical, and then the SQL. Okay. So my API is no different. So on the killer video applications, you can create some video and put some comments on the video. So 2 entities, user, video, and we will provide comments. I put here the attributes. This is my conceptual data model. I have my application workflow, a couple of queries. Because I have 2 screens, on one screen I will show all the comments for a video. And on another screen, I will show all the comments for the user profile page. So, of course, 2 queries, 2 tables, and all the CRUD things, but there is no big deal about it. So using the mapping rules, you will then create 2 tables like that. Use the different attributes, you get your logical data model. Okay, so far so good. And you see maybe that, oh, you have a creation date and a UID. Maybe you can merge those one using a nice time UID. Well, it's just the physical data model optimization. And at last, you get your DDL. So for now, you probably didn't learn anything. But this is those tables that we will use for the API and the services. Again, yet another link to remember. All the steps I went through, you can do that. You can do the same using kdm.dataview.org. So I can try to show you up. So it's free, even if it's written, try KDM. Again that. I'm prepared. Come on. Okay. I know. Okay. So you won't see the KDM, but okay, probably just define that and following the tabs. Oh, okay. Help. Oh. No, I'm root. I am the root. And as root, you can go SSL. Oh, what the okay, KDM, try. Oh, it's better now. Yeah, so there are a couple of available model like here. This is a use, what I pick? IoT. Okay, IoT with a sensor, a network. You provide a couple of queries, 1, 2, 3. Then you get the logical, the physical, and boom, you get the SQL. So if you don't know that that exists, you should have a look. And you have to make your user and developer maybe use that just to have an overview of how to have a proper data model. So nothing very crazy. I won't switch again, just. So we got the constructed data model. We have the queries, and we know that we will use Apache Cassandra, no surprise. And so, which is the best for each use case? Okay, so can you still hear me? Yes, we can. On the stream, right? Okay. Okay, single hand. Or maybe help again.
Fixing bugs in production.
That's nice. I will come back. I like it. Okay. Let's go with some Docker compose up dash t. So I will start 3 containers. The first is, what a surprise, Cassandra. One is a studio and one is Op Center. So demo effect. So expect that it will fail. And if it's not, we are lucky. Okay, so this is a server. It's starting. It can need a couple of minutes to start. Okay, so here it is. Okay. And I will try to, oh, I don't need that anymore. I will try to go to, I try, it's not ready yet. It's coming. Have you ever tried to work with Docker using Apache Cassandra and waiting that the database is ready before starting to create the key space and the tables, and try to poll and do some, describe schema, describes full schema again and again? Okay, it's getting a bit long, maybe. So what I do, I just set up Op Center to use my huge single node cluster. So it's should be okay. I don't have to install the agent because, well, it's already available in the Docker image, and it's, come on, it's still starting. But I want my, maybe because I just, I should be fine now. So I will also start the DataStax Studio, and okay, I will open an existing notebook just to say, okay, I will describe existing key space, and I will create the very nice table we just defined together using the process and the SQL stuff. So if I go there and see, oh, now I have my 2 tables created, we're good to go. Let's have a look on our cluster. Is it better now? It's still okay. It's still starting. We will come back. Okay, so the database is there. We have created the tables, but we don't have any data yet. So I will use my French method to generate some totally random comments in the tables. It will generate me a user ID. I will keep that for later. And just for you, I just generated some totally random event. Just okay, couple of events to work, because we will have to look at that to the API. Okay, so 3 techno. First techno is REST, the most used and still used right now. So I have a multi-maven project. Let me shut down that. I don't know if it's big enough. So let's go to the REST and start the REST API. Okay. Just during the application starting, REST is pretty easy. It's well defined. We have some books to know how to properly implement an API using REST. And so this is what I did. I reuse resources, HTTP verbs, and open API / Swagger way to implement an API. And okay, to implement, give me the list of the command for your user. Give me the link of the command for video. Here it is. Give me the list for a user. Give me a list for a video. It's a query. It's a get. And you need a user ID. You can go here, try out. I want a user ID. I create one user ID here. You can go here and you can try, and you will get your comments. Woohoo! Okay, so REST is easy. When it comes to create, delete, put, you put the correct JSON. It's JSON over HTTP. And for get, okay, so far, when you want to list all the comments, it's fine, but we are in Cassandra and we don't want to do some select star in the table. So you have to provide some filters, some params in the query, some paging size, and REST is not very good for that. You can do it your way. You can do everything with REST using page size and page state. Page state to provide okay, I want only 2 items. So I will again try, execute, and then, Cassandra provide me the paging state. And if I want page 2, I will just provide the paging state here. State that page 2 is also using size 2, and we're good to go, and we get page 2. Okay, nothing crazy. You have the code. You have everything you need to run that demo. It's embedded in Docker and just running in your IDE. Just Maven Spring Boot run, and it's running. This is actually the purpose, to provide you sample code. Okay. gRPC, who are already using gRPC in the room? Okay, not that many people. So it's provided by Google. It's work on HTTP/HTTP2 protocol. And it's all about performance and asynchronism. You get it? I think. Okay. There is no UI, so it's pretty. I will go fast here because after that I got the decision tree to draw for you. So I need a user ID. Here it is. Look, I am doing my demo with one hand. Isn't that crazy? Here we are. And I run a GUnit, and we're happy to see that I have the very same result getting, but it's very close to REST. It's close to SOAP. It's using not REST. It's close to SOAP. You provide some contract using proto files. Like here we got a sample. So you will define your entities, and you will define the different method and services and function. High-level function you want to invoke. So it's really command-like. it's not really CRUD. You can of course edit or change an entity, but you can see that if I want to update a comment, yes, I will have to create a dedicated method named comment on video, like we used to do with SOAP. And okay, you can do it, but this is not the best things to do. The best things to do with gRPC is to invoke service and action like API. Okay, and last but not least, GraphQL. Let's go. So you have to. Okay. Okay. If you are under 25, you probably heard about GraphQL. And if not, and if you're older, you don't. So it's actually a thing for young people. Actually, people working with front end and JavaScript and such, you will define your contract. So you will provide GraphQL stuff like that. I know this is a query. Sorry. Okay, so you provide a schema, and the nice thing is they use the proper word. We know that what is a mutation, and so now you know that we will split the read-only queries and the mutation queries. And a bit like gRPC, you will provide your entities and your query. And this is nice, because the first time people told me about GraphQL, they told me, oh, it's magic. You just plug that on top of your database, and then you have an API working. And tools like Prisma.io provide you a full working GraphQL API on top of RDBMS. But what does that stuff do is actually each time you look in a table, you get a list of item, and if you need to search for the joins and the relationships, you will have an n+1 select. So it's very nice for the little young people developing front end, but for you at the back end, n+n joins select everywhere. So I say, oh, it's not for Cassandra. And actually, you can specifically provide and list what are the only available queries. And such, you can hope that your little young developer will query using a partition key and not the select star. Hopefully. So, oh, we don't have a demo. So let's go back here, and I have a user ID for you. Let's go to the demo. Okay, execute. Woohoo, and you got the same thing. Nice thing about it, first, you have the documentation for you. You can browse the documentation and see what are the methods available. And as a developer, you can also select which field you want to get as a result. So if now I say I only want the comment and execute, then you get only the comment. So that's nice when your customer client cares a lot about the bandwidth for mobile. And this is the reason, the main reason that stuff is working so well, because it's using by jeunes and young people and JavaScript everywhere, and mobile. And actually, this is the same guys. So it's working quite well. So now let's go back to serious stuff. We are architect, and we want a proper decision tree. Which technology should I use in which use case? So let's go. First, we need a serious list of criteria. Okay, so we use cardinality, versioning, confidentiality, atomicity. Okay. Filter, paging, throughput, latencies, very important. Integrity, caching, synchronous versus asynchronous, SLA, very important. What about the developers? Okay, do we need an API catalog? Which language can use my developer? Do I need to test, build, package? document. And of course, if I know my customer or not, you can have an internal or external API. You can choose the technology. Okay. And as old technical ivory tower architect, you will define a matrix with weights and say, oh, for that use case, this stuff is okay. And you finally got a nice decision tree. No, we won't do that. Instead, just a couple of principles. I already told most of them, but for REST. REST is good because you're decoupling client and server. It's schema on read. So you will query, post, and read only what you need. For API lifecycle, it's very nice because you can use versioning, provide version number in the URL. And as is now the new soap, I read an article say REST is the new soap. So there is a lot of tooling around REST. All the API management stuff, it's based on REST. And even now, the function as a service and serverless expect the endpoints to be REST, so it's everywhere. So it's nice. It's working pretty fine. You can do everything you want with that, but it's verbose. You see the JSON. It's still better than XML, but it's still JSON and a huge payload. You cannot discover. You can use some extra tools like I did with Swagger, but by default, you have an API on the endpoint and you don't know how to invoke that stuff. On the contrary, you see with GraphQL that you have everything available for you. And it's good for CRUD, but not when you want to execute a command, an action, processus. So again, if you take a picture, this one is okay. So REST is a CRUD superstar, and even in Jeepster framework, which is a scaffolding tool that will generate for you a full working application based on entities and queries. What a surprise! So it's relevant for LTP, not that much for OLAP. So it's good for public and web API, but we all already know that. gRPC, okay. It's good for high performance, based on HTTP2, full async if you need to. That stuff will generate for you 3 stubs, synchronous, asynchronous, and even bidirectional streaming. As it's serialized using protobuf, small footprint, and fast serialization. So it's all about performance and streaming. But it's strongly coupled. You have to provide a file proto and generate stubs. And maybe if you already work with protobuf, you know that it's seriously limited. We have to provide the list of the field one after the other and get some ordering of the fields. And yeah, protobuf is not that good. So you should use gRPC for distributed network of service. Thinking about Netflix, for instance, or Google, the service won't wait. They will invoke one to each other. They have a full grid of microservice, but they won't wait to each other because it's full async everywhere. And that stuff works very well for high throughput and streaming use case. And command like when you do Slack, you post a message, you execute some stuff. It's not it's not CRUD like API. And GraphQL, same. What I like is discovery documentation, the custom payload, if you are a mobile developer, and match the standard. So they won't break, young people won't break things yet. They will, but not yet. But there are some serious drawback. There is only a single endpoint. That means no versioning, everything on the single endpoint. You cannot monitor each resource has been invoked. It's always the same resources. So if you want to do some monitoring, you have to explicitly implement that stuff in your code. So all the nice features providing to you by API management or proxies on top of the API, You cannot use that very easily with GraphQL. You can, but it won't provide fine-grained monitoring security for each services. It's still complex. I didn't show you it's a Java implementation here. Node.js is, of course, the most advanced here. But in Java with Spring Boot, it's moving very fast. It's still not yet very dry. So we should wait a little bit if you want to use Java. But it's a young people thing, so use JavaScript. So yeah, and my idea is that is nice for customer, but not for DB engineer with the nasty n plus un select, or you specify explicitly each query are available or not. So backend for front end, no surprise. It's good also for service aggregation and composition, because if you have multiple services around your IS, you can put some kind of proxy on top of it, and then your final customer will reach that proxy, list exactly what they need, and the GraphQL backend could do the composition for you. It's most of use case right now. Actually, backend for front end and service composition, it's pretty close. This is actually what it means under the hood. And when volume/bandwidth matter, of course, if you can select which field you need and which you don't need, then you're happy with that. And that's it.
Hello. I have seen that you have mentioned about Internet of Things. So why do we need to use Cassandra as a database for Internet of Things? Why not Prometheus or Inflex for time series?
Oh, for time series. Okay, there is nothing to do with the with the with the presentation actually. So Apache Cassandra, I know, is of course very well suited for time series because you can have very high throughput and very high volume. And using the sensor ID slash symbol, you can easily define some partition. Yet, as you said, there are some limitations. You cannot edit some listed like you would do in InfluxDB. So I would say Apache Cassandra is a general NoSQL database very well suited for time series, but not only that. It's not only dedicated to time series. In the DataStax Enterprise solution, on top of the Apache Cassandra, we also provided the Solar in the same JVM, so we indexing the event, and we are able to do some search. By default, you cannot do that with Cassandra. So if you know that you already only have to use some time series and that's it, and not that much volume. I don't know how much InfluxDB can scale, but I know that Cassandra can scale with linearly. Ouais, c'est linéaire, quoi. I'm pretty confident with Cassandra using the linear scalability. And I also know that when you work with time series for the, let's say, 31st day, you want to do some OLTP stuff. You want to draw some nice curve. But after 30 days, what you want to do is analytics. You want to do some full aggregation and of course, in DataStax Enterprise, you have Spark to do that. I'm not sure that you can perform some OLAP queries on top of InfluxDB.
Thank you, Cedric. We're going to have Matt Heath now from Monzo. Hopefully this time it'll work. Different laptop.
Yay.
Hello. Sorry for keeping you all waiting. Replacement laptop. Don't know what happened to my other one. Wanna start? Yeah. Yeah. Cool. Okay. Okay. Off. Yeah, thank you for coming, everyone. First off, my name is Matt. So I'm a backend engineer here at Monzo. Thank you all for coming to Monzo's HQ. It's amazing to have people like interested in Cassandra again. If you have any questions, I'll be around. Otherwise, I'm here on Twitter. So give me a shout with anything. And yeah, I should probably preface this with I love Cassandra. It's amazing. However, it has caused me an indescribable amount of pain over the last few years. But without further ado, I work at Monzo. If you're not aware, we're a bank. Given we're here, probably do. And yeah, our mission really is to like make money work for everyone, and that means making finance accessible for everyone who is traditionally excluded from a variety of financial products. Really, it's quite hard to get a bank account if you don't have a fixed address, for example. But also to help kind of people understand their money and help people understand how they could save money, or maybe we could help people save money. Those are the kind of things we're aiming to do. So to that end, we have an app, we have a hot coral, debit card. And the main aim of our app really is to deliver sweet emojis in real time. There's an indescribable amount of code that deals with emojis. So yeah, like when you purchase, there's like a certain amount of magic if when you tap a card, you get a push notification like immediately after, sometimes before the receipt comes out. And a lot of that works off Cassandra. We have loads of queues, but like essentially all of the data we store here is stored in Cassandra. And yeah, we can talk about that in a bit. So over time, we started the company in February 2015. We launched our initial alpha cards in November 2015. So we only had 3,000 printed. We really didn't think anyone would actually want one. They weren't very good compared to a bank account, couldn't make payments to anyone. So the first like few hundred, we kind of like forced people to have. And so like not very much growth here. Pretty much use any database for that. All good. A little bit later, we got our beta cards, at which point we started giving out quite a lot of cards. We were doing events. We were starting to post them out. It was a lot of fun kind of packing them into envelopes every day in the office, which is like just up the street. And then once we launched our current accounts, we brought everything in-house, and things rapidly spiraled out of control. So at this point, I think we're the fastest growing bank in the UK. We have 1.6 million customers, and everyone who is moving their money through Monzo is very heavily depending on Cassandra and our usage of Cassandra, which is awesome because it gives us so many benefits. But the real question is like, why would we even care about using Cassandra? Why a distributed database? The main aim behind our platform is to be a cloud-native platform. If you imagine the kind of insanity that happens whenever Netflix isn't working, like people go, they like want to watch something on TV, nothing works, cool. But somehow banks get away with that level of availability. Banks have outages all the time. They have extended maintenance windows. It's apparently okay to have maintenance windows overnight, over the weekend, down for the entire weekend. Like that's a kind of practice, and that just doesn't make sense to me. I don't understand why can I not speak to my bank at 2 in the morning? And that's the kind of service that we're trying to provide. People work different shifts. People don't have time to do that. Like if you work 9 to 5, you basically can't visit a branch. But equally, if you work shift work, like it's difficult in different ways. So this quote from Adrian Cockcroft a long time ago. I think some slides like 5 years ago. And it still very much applies to our entire platform. We're trying to build a highly available service on top of a load of components that are probably broken sometimes. That's kind of inevitable. And Cassandra is one of those things. It allows us to have high availability and kind of tune that quite a lot. So how does Monzo operate? We run on Amazon, Google Cloud, and we have physical data centers. Turns out you can't plug fiber into a cloud yet, which is quite annoying, but hey ho. And then we use a load of other technologies, Kubernetes, kind of everything runs on pretty much here, and a load of other stuff. As I mentioned, pretty much all of our data is stored in Cassandra. All of our services that access that are written in Go, pretty much. I think we have like somewhere like 5 or 10 Java and Scala services. Everything else is Go. And that has also spiraled out of control. So we now have 947 services running in production. And that the pace, as you can see on that graph, is increasing as our team gets bigger. So who knows what that'll be like in 6 months. And to put that in perspective, about 400 of these use Cassandra. So that means at a minimum, we have 400 key spaces. The last time I checked, we had like 12 or 1,300 column families, tables. And none of these services can access the other ones. So it's very much a kind of hard limit between each of these with HTTP calls between all of them. However, I didn't always like banking. I started using Cassandra 6 or 7 years ago at Halo, which is a now defunct taxi app. And Halo, we moved from a world of like MySQL to using Cassandra at the point that we expanded internationally. So we had a kind of interesting model where people could use their customer app both in the States and in the UK. And we wanted them to have relatively low latency, but also kind of independent failure zones. Thankfully, replication time, you can only get between the States and here in about 5 hours. So as long as you can replicate someone's data in 5 hours across the Atlantic, all good. And in our case, we ended up running in a load of different cities around the world. So we had kind of our initial infrastructure that ran across 3 Amazon regions with a Cassandra cluster that spanned the whole thing. And then later we had a separate platform that ran across 2 regions, equally with a whole set of Cassandra clusters that ran there. And that for me was like amazing. I could build things that were really scalable, but also highly available. And I didn't have to deal with like MySQL replicated log failures. It's pretty great. So a while back, then I got kind of pulled into this world of banking. And my immediate thought is banks are not very highly available. These people need some Cassandra. And clearly, like Cassandra wasn't around in their day and age, but like it's here now, so we can use it. But the main reasons that we would use Cassandra here are because, again, it gives us high availability. We can have multiple failures, and people can still use their cards. They can still use their app. That's incredibly important for us. You can't withdraw money at like 2 a.m. and it's because you're kind of lost and you know where the ATM is, it's right there, but you have no ability to get cash and no one will take cards, like, and you can't get home. That's a problem if your card doesn't work. But also, like we have a lot of different operations. We don't need strong consistency in a lot of cases. Kind of a interesting concept, banks and strong consistency. We can talk about that at length if anyone's interested. We want to be scalable. We're kind of hoping we would be this really successful company, but like probably not, probably die. All startups do. And at some point in the future, if we were going to expand internationally, it would be useful to be able to replicate our data, obviously within data locality laws. So the thing that we kind of have a fairly basic, like normal setup within Amazon. We have 3 availability zones. We run like network topology strategy for the vast majority of our key spaces tables. And then that means that our data is distributed. Great. We can lose 1 copy. I'm like, cool. I can lose an entire availability zone. And like, yeah, I can still sleep at night. All good. Lose more than that, then we have some problems. And at that point, we're not relying on Cassandra to deal with that. We can put different systems in place to kind of deal with those kind of failures. However, one of the most interesting challenges that we've had is data modeling. And it's obviously a topic that's talked about at length. As Sarah said, like it's the first thing you need to think about when you're building your applications. And there are many reasons for that, which we'll go into. And this, I should maybe preface this with, this is actually like a hard problem if you are a company that is trying to hire lots of people. So if you want to hire lots of engineers, what percentage of engineers do you think would have experience using Cassandra versus Postgres? So if you're building an engineering team and you want people to be super productive on day one, like most people know how to write SQL queries or like use a norm or something. That those things make complete sense. And it means it's a very big data shift, like mental shift to, you have to think of all of your use cases up front, because actually in a couple of years, you might not be able to re-index your data, or it might take several days for you to iterate through every single partition just to copy it somewhere else so that you can read it to add this tiny feature that you wanted to do. It's very annoying. And that's hard as that like kind of mental shift for people. So classic cartoon here. When people ask me how you should query it, this is the response. You write a distributed MapReduce function in Erlang. And this cartoon's been around for years. It's still one of my favorites. Because like this is basically what people say when I'm saying, oh yeah, you need to like denormalize your data and you should do it this way and it'd be great. They're like, why would you do that? That makes literally no sense. So saying that in like a supportive way is probably the first step, like helping people go on that journey and helping people understand why data modeling is important. When they're like, I would like to store 10 megabytes of data, you're like, well, we're going to put it in this really highly available database. It doesn't need to be available. Yeah, but like standardization, it would be much easier for everyone if it was in the same database. At that point, it's a bit of a trade-off. But by having some form of standardization, it means people can move between teams quite quickly. Anyway, so standard kind of pattern, if we have a table, we have like an ID and a set of columns. Cool. So this is a standard database table. Everyone understands that. Pretty easy. Obviously, you can't do select star where b equals thing, but like that's okay. So in our case, we would use this in loads of places. If you, I'll come back to that in a sec. If you are having an account, you might want to load the person's account. You know their account ID, you can load their account. Great. Cassandra is going to store this as a series of columns, the value for each one, and then the timestamp. And the timestamp is quite interesting because that's what we're using for conflict resolution. So if we have multiple writers writing to the same thing, in theory, if depending on certain use cases, we could write that quite nicely to only update certain fields. In practice, it's often easier if you have a framework to just like write the whole object again. And that's a problem because now you've actually only changed one value, but the conflict resolution is updated on all of them. So kind of, again, like changing that model of I want to mutate these two things, I have to apply an actual mutation rather than I just save the object. Again, that's the thing that is like a mental shift. So this is a fairly simple table we might have. We might have a table of accounts, bank accounts, fairly straightforward. We'll have an ID. Every user would have a user ID, so we will have a user ID who essentially owns the account. Some of you might have a joint account. You might immediately see where this would fall down. So yeah, we had to change this when we launched joint accounts. So initially we had like a user ID on every one. Now we have like a permissions model. We knew we'd have to build it at some point, but joint accounts was the part we had to do that. But if we consider a slightly simpler model right now, we might have a set of accounts that's owned by a person. And in this case, we'd have a primary key of the ID. So we can look up that account. We can see the currency, the country it's in, get a description, that kind of thing. So in this example, we would have the partition key as the account ID, and then we'd have a set of columns, created description, user ID. Great. So we have some stuff, and we have the timestamp. Now, timestamp's quite interesting if you're not using Java as your client, or if you're using a language that maybe doesn't have the same time precision. CQL shell, for example, doesn't show you the microseconds that are on this value. So if you like do select thing, it'll show you what the column is, and if you copy the precise string it has, and then do a select on it, you don't get any data. Yay. That is not obvious, and that's not obvious to a load of people. And it's also an oddly hard thing to Google. You're like, why does my timestamp not equal this timestamp? Who knows? So that's cool. So you can read by account. But one thing we can't do with this particular data model is get all of my accounts. And the first version we wrote of this, we didn't even bother. We did a range over all the rows, and we found your account because it took about 2 minutes to write that code, and our library didn't really support like multi-key partitioning that well. So yeah, that worked well for a certain amount of time, and then obviously we had, I don't know, like 1,000 customers, and then it didn't work very well. So clearly, like a better way of doing that would be to have some form of compound primary key. So we're going to partition by the user ID, and then use the ID as a clustering column, and we'll get the set of account IDs effectively. So we'll have a nice kind of structure like this. So we'll have our user ID as the partition key, and a wide row of rows, which will be people's accounts. Cool. So a partition key, for anyone who's not aware, I'm going to hash that, and that's going to determine which node that goes in, which vnode if you're using vnodes. And that's cool because, well, it's cool until this point. Because it's going on one node, your entire partition and all of the rows are going to be stored on one node. So if you are unlucky enough to index something, a lot of things under one partition key, you're going to end up with one node with all the data, everything else doing nothing, and no ability to shard that again, really. Thankfully, that's not a problem because no one has infinite accounts. Yeah, all good. Apart from if you add transactions to the mix. So in this case, we again might have a transaction. A transaction is something you would see in your feed. So we actually have feed items, and then a feed item may be a transaction, and that may have its own ID. And in this case, again, we can look one up by ID. And that's really useful if we're doing kind of payment processing operations. We don't need a whole set of them. We need one, and we can do things like that. So again, we have a normal kind of map table, lots of columns. But we, again, have to know the primary key, so we can't iterate. So we can't even show you a list of your transactions with this model, which is a problem. So in this case, we could partition by the account ID. So we'll get a wide row of a person's transactions. Now, there are lots of cases, transactions might be an obvious one that this will break. But there are lots of cases where you might think that is an entirely reasonable thing to do. As an example, in our app, we allow you to see which of your friends have Monzo. Now, we don't send your contact book to the server. We do a kind of dual-way hashing model where we send part of a hash and we get a set of hashes back, and no one can determine whose data the other one has. But if we stored all those hashes on your account, you'd think, cool, like how many people do you really have in a phone book? A couple of hundred, maybe several hundred. Some people have tens of thousands of contacts in their contact book. Tens of thousands. So many so that we originally sent the hash, which was relatively short, as a query parameter in as like a get request. And ELBs in Amazon don't have a limit on the query length. ALBs do. It's like 65,000 characters, but they do. So that would break that feature for a load of people. In this case, that would possibly break our model here. So why is that a problem? In this case, we're going to have an account ID, a whole set of transactions. We're going to go to infinity, basically. And there's like a slightly interesting model here where if this becomes really slow, you've actually made the product really slow for your most enthusiastic customers. Because if you only have a couple of transactions, it'll be really fast, it'll be fine. But the more and more you use the product, the worse it gets. And that's really bad. So this is clearly something that doesn't work. So time series to the rescue. So a common thing that people say is that Cassandra is really, really good at time series data. In some cases, that is true. In lots of cases, that isn't true. So the problem you have is if you have like really predictable data, totally fine. So to start off, we'll take, we've got like a set of transactions here, kind of order by time, and we'll use a partition key that will compute. So we'll take the account ID, definitely still partitioning by account, and we'll truncate the time to a certain bucket. So we'll pick a certain amount of time. Now, actually, a really long time ago, we thought it'd be useful to be able to iterate all transactions in some of our internal tools, you know, so we could list recent transactions and do some kind of interesting UI things. That meant that we had a time series where we had a bucket of like 2 hours for all transactions, and we had a bucket of like, I don't know, 30 days for normal people's accounts. So in this case, we'll split by account ID, apart from that other table we'll come back to in a sec. And we're partitioning by time, so say 30 days, and we're using created time, so the timestamp as the first clustering column, so within the row where we sort it by time, and the ID for uniqueness. Cool. So we'll have like a bucket of, let's say it was day 1, we'll do 1 a day. In this case, we'll have day 2, we have another partition, and we have lots more, and that's great. So if we're going to like read those back through an API, we're probably going to start at a point in time and we're going to work backwards. And you could do paging by time, but you're going to start at a point and you want to return some number of transactions. Fairly common API case. Cool, so that's fine in this case. But what if the person didn't purchase anything on day 2, or if they didn't use the product for like 2 years? Do we even know that they bought something on day 1? Like, when do you stop iterating backwards? And with this kind of model, you have this problem where you either define the time bucket to be really big, in which case you'll have a small number of buckets, and you'll probably get a hit for most of them, but they'll be big. Or you have a small set of buckets, which means you have loads, but it's highly likely most of them will be empty. And so a lot of the use cases are like sensor data. At Halo, we took the driver's app would send a GPS point every 5 seconds. Super predictable. Like you know exactly how much data is going to go into each bucket. You can decide your bucket. You can size those things up front. With models where you're entirely based on the user's interaction with a product, that's much harder. You'd have to like guess, and at some point in time you might be wrong. So in the example of our time bucket where we used 2 hours for all transactions, as you might imagine, that worked really well to start with. And then, to be honest, even once we had some amount of traction with the prepaid product, that exploded. And it exploded because all of that data is stored on single nodes. So if you have predictable data, time series are great. How you choose your bucket size, you can kind of do some like back of napkin calculations. But you need to work out if that's going to grow and change over time. So in this case, day 2, we have a slightly different problem. So if we went back to that model where everything is going into one bucket, and we've even made the bucket really small, like 5 minutes, that means everything, like all domain entries, are going to write to this partition for a 5-minute window. And once that boundary ticks over, it will move to a different partition key and everything will write there. So if you imagine that you have a laser that you're going to point and it will change location, change destination every 5 minutes, you'll like destroy those 3 nodes, then those 3, then those 3, etc. And the problem we would see with stuff like this is you'll build up loads of stuff and you'll maybe trigger compactions as you hit like the SS table boundaries and that will compact them together. So you'll like write shitloads of data and then the data will move away and the node will be busy while it compacts. And hopefully that will balance out before another hot partition is like on that node again. So this is again a problem with time series. If you are doing a really basic, here's the time bucket, depending on your replication strategy, you're essentially selecting which nodes are going to handle all of your traffic, which isn't ideal. You could scale to however many nodes you want, have a 1,000 node cluster, and 3 of them would do all the work. And yeah, it would move around, and that would not be ideal. So we had this problem, and like determining how you then do that is much harder. So we've ended up with a kind of model where we had an additional shard component for certain hotkeys. So we'll have like a time bucket and a sharding component and a partition key or multiple partition keys, which then means like you can write really, really well. You can scale your nodes out fine, but now you just have a different problem reading. So again, you have to read from all the different ones. One of the things we did at Halo here for the previous problem was we actually had, for an index, which had a set of partitions, we had an index, which essentially was a wide row that told you which partitions existed. But that had different problems as well. You have essentially a wide row again. So one of the other things we have at Monzo is what we call a flake series. So in the example I had with a time series, if we have transaction 19 here in the middle, and it's in a table that's ordered by time, and you'd like to read transaction 19, you have no other option but to denormalize the data. You have the ID, you have no idea what time it was created, so you'd have to go to a table. And that means if you want to update it in both places, you'd have to read from that one to work out what the time is, to then be able to even update the fields in the other one. So you can't even just do like a mutation, you have to do a read them right. So one of the ways that we achieve this is by kind of encoding this into our IDs. So in this example, we have an account ID, a time bucket, a created timestamp, and an ID again. What if that was something we didn't need? So I don't know if anyone's used Monzo's API. No one, great. So if you do, or if you ever like see like some of these like identifiers, you'll see that we don't use like integer IDs. We don't have an auto-incrementing number system. We're not using MySQL or Postgres. So we have to build a system to create IDs for every object. And because we run in a distributed system, we have to provide lots of guarantees that they are all globally unique. So we have an ID system that generates IDs like this. And that looks insane. However, in this example, it's based on time. They're also lexically sortable. So you can sort the IDs like alphabetically. And actually, as they increase, that actually is the time ordering, unless you created them like a few milliseconds apart and there's some clock skew. So it's like k-sorted. So in this case, it's actually a base 62 encoded 128-bit int, like that. And then that is primarily the top 64 bits of that are the time in milliseconds since the epoch. So the worker ID, we're running this in Kubernetes, which guarantees uniqueness on the worker ID. And the sequence ID is incremented for every ID you generate within a millisecond, which happens surprisingly often. So we run a number of these. In theory, they can generate up to like 4,000 IDs per millisecond. I think we're okay on that part. Some of the examples, I think Twitter used one that's Snowflake. It only has 64 bits, so it has like a truncated custom epoch. So we did consider that. I'm kind of hoping a bank stays around for longer than 68 years, which is the maximum ID range if you use a 64-bit one. I mean, I'll probably be dead by then, but it's really not something that we wanted to like have to deal with. So in this case, we don't have to even do coordination. We don't need locking on things. Our like Kubernetes gives us worker IDs that are unique. We don't have to maintain like a lease on an etcd worker or like Zookeeper or something like that. So with this level of ridiculousness, we actually end up with an ID that's a string. So we could have a map table that we put that in and we can read the columns, great, because it's just a string. For our transactions, we might have something like this. So again, a similar one. We use prefixes, but actually the IDs themselves are still globally unique across all object types. And they have padding here, the zeros, again, just to make sure that over time we'll use more of the digits, and that's the maximum range you need. So in this case, we no longer need this. We can take an ID. The created timestamp can be extracted from that. So we know the creation timestamp. We can truncate that to get the bucket, and we have the ID already. So actually, with one ID, we can use one table as a combination of a time series and like object storage. And in this case, we would then do that partition by account ID just to make sure they didn't get too big. So who here sticks TTLs on their data, like on columns? Cool, a few people. Great. Yes, we've had a shared experience of this. You can probably see where this is going. So we use TTLs for lots of things. At Halo, we use loads of TTLs, and it was really useful. If you imagine, like, if someone's driven you on a taxi ride, then you have lots of GPS points that go along that. But you don't need that level of granularity, like, forever. So we would write all the points as we recorded them, and then we would update the TTLs to essentially have points with a set frequency that had like a year-long TTL. And then between those, a few that had like a 3-month TTL, ones in the middle that had a 1-week TTL. So if you were looking at a map and you looked at it a couple of months later, it would still look the same, but it would have like fewer data points. And it would slowly lose granularity until a year where we didn't need them anymore. We stored so many GPS points, it was truly insane. I don't know how many trillions, it was crazy. However, TTLing your data is not always a great experience. So if you imagine we have this kind of thing and we have a set of columns where we've mixed the TTLs across these. So we have some of them that are going to expire in like a couple of minutes, some that are going to expire in a few hours, and some that will expire in days or maybe even weeks. And the one place that we originally used this was one of our logging systems. So we have like a log aggregation system, stores the data in Cassandra. We have like debug or like trace level logs get stored for, I don't know, a minute. Errors get stored for weeks. So as the log lines come in, they're like indexed by their request ID and a few other like indexes. So we have multiple different partitions. And then each one, we again want to like slowly age out the less important stuff and keep the important stuff. So the problem we have here is they have all been compacted into the same SS tables. So when our first logs expire, we've like lost a few. It's great, they've been deleted. Everyone knows that when you delete data from Cassandra, it's gone. Yeah. So in this case, we've written a tombstone, and that means that the default grace period is like 10 days. And on our logging cluster, at some point that didn't work anymore, so we changed it to 1 day. And that didn't help much either. So at this point, what you're doing is, once the TTL has expired, in theory, is now that row is eligible for compaction, like deletion when it's compacted. But unless you actually compact the SS table, it's immutable. So you're never going to actually delete the data. Cool, so our first set of unimportant data has expired, it's gone. The next set expires, again, great, gone. But of course, all of this is still on disk. So that's a bit of a problem. One, because the data volume doesn't decrease. And if the files got bigger and bigger, you might only have a periodic compaction. So yeah. And we've had this in our logging cluster. We also had another one where we didn't have like throughput issues, but it just meant that the data volume on disk was much larger than people would have expected, and it's because nothing had been deleted. So in this case, we've switched to time window compaction strategy. So we create a new SS table for each time range. That's configurable, and within that, you'll do level compaction. So that means that we would have all of the things in bucket 1. Once that point in time has gone, all the SS tables are essentially deleted off disk. That's great. Now, within that window, you might have expired other things, and they still won't be deleted until like the files themselves become eligible. And that can still be a problem because there is a certain maximum number of tombstones that Cassandra will iterate over, and then it will give up. So if hypothetically you had deleted more than 1,000 rows within a partition, it'll just stop at that point, and you won't get any data back. However, if you've written this kind of thing, then once the next set expires, again, that'll be deleted off disk. And once the third one goes, everything will be deleted off disk. So this gives you at least kind of a bounded range where everything will be deleted. However, it requires you to think about this when you're modeling the system. You need to know, am I putting all of the same TTLs into just like one table in one partition? Could I split that up? Are they going to have different properties? And in this particular case, our cluster is essentially dead because we have a web dashboard which was querying a pretty wide time range, and that would iterate over all of these, skip over like tens of thousands of tombstones, and then eventually die. And of course, once it died, the thing would get a 500, so it would just retry. And it was in like a really tight loop in JavaScript, so that was a problem. So yeah, a few takeaways. I think one of the things that is like generally talked about with Cassandra is that data modeling is incredibly important. But like in practical terms, it really is quite important, and there are so many things that can go wrong, and so many things you might not predict. And maybe that's okay to a point. I think if we'd taken the time to try and predict and fix all of these things on day one, then we wouldn't have been able to build lots of other stuff. But certain things are yeah, definitely worth checking out front. Wide rows are an obvious one. They're okay until they break, and there's very little warning before that happens usually. Repairs on these are really problematic. So as an example, one of our wide rows is about 45 gig. And yeah, I thought I'd seen it bad at Halo where we had like one that was like 17 gig. You're like, oh yeah, we put all the events for a time in like one thing. Like, never do that again. Sometime later, yeah, we hadn't even realized, like, but a number of partitions that were like relatively hot just had slowly increased over time. And this is for one time bucket. It's one wide row, 45 gig. And at that point, you can't repair it. Like the amount of anti-compaction that happens and like the amount of data that has to be synced back and forwards between the nodes just doesn't work. Thankfully, that one immutable, write only, append only. So we could essentially rely on some amount of repairs and then, to be honest, anti-entropy to deal with that particular table. And that has now been fixed with sharding. Yeah, so repairs don't work on really big partitions. Making time series buckets predictable is hard, and that really depends on your like use case. Hotkeys will break everything, including your sleep. And yeah, TTLs often don't mean that your data's been deleted. But I think mainly, like, yeah, what works there probably won't work there. But that's maybe still okay if you could fix it somewhere in the middle. Yeah, I think that's it. Yeah, so can you run a bank entirely on a distributed transactionless database? Yes, you can. It requires a lot of work, and a lot of that work is thinking about how you model the data, and a lot of the work is like some of the kind of inconvenience having to deal with like manual denormalization for actually relatively small use cases in lots of places, when the bigger use cases are handled really well by Cassandra. But yeah, ultimately, if we hadn't have used something like this from quite early on, I guess like we're 4 years in now, so we'd probably be doing that now. And migrating a running bank across databases is really not something we wanted to do. So yeah, Cassandra's worked out incredibly well for us. And yeah, that's it. So I think we've run out, unless we have any questions. Yeah? if people need to leave, like, I realize we're like over time, so don't feel shy, like, talking away. Questions, anyone?
So you mentioned the analytics. Do you use Spark overlays over Cassandra or completely separate analytics solutions?
So our analytics is actually based on BigQuery. So we have an event pipeline. Monzo is kind of a mixture of synchronous calls, which kind of power your app and do like real-time payment system requests. And then everything else that we can do is entirely event-based. So we fire events, those go through Kafka primarily and drop either into Cassandra in a number of cases, or we pump them into BigQuery. So we have some use cases that are based on Cassandra. They're usually like per user things, so the volume of data is comparatively small. And then, yeah, most other things, we essentially stick into an SQL database, but one that's really big that we could never afford to build. No other questions? Cool. Oh, yeah. No? Great. Okay. Well, thank you very much for coming.
Just wanted to apologize for the technical issues that happened before, and thank you very much for staying until the end. And I hope you all have a great evening, night. Thank you.